Haodong is currently a third-year PhD student at Multimedia Lab CHK, supervised by Prof. Dahua Lin. His research interests are video recognition and human-centric action understanding. Before that, he received his bachelor degree from Yuanpei College, Peking University. He is also a main contributor to OpenMLab. So let's welcome Haodong.
Okay, so hello everyone, and my name is Haodong Duan, and I'm a third-year PhD student at Multimedia Lab CHK. My talk today is about action recognition in a human-centric view, and in this talk I will share some research projects on this topic. Yeah. Okay, let's first look at the definition of action recognition. Action recognition aims at recognizing the human action in a video. And so compared to images, videos have an additional temporal dimension. Thus, they have rich modalities. Here we demonstrate 4 modalities in videos, like the RGB frames, optical flow, scatter, and audio. Among these modalities, scatter is a coordinate sequence of human joints. It is a compact representation that is closely related to human activities. The scatter-based action recognition has received increasing attention in these years. And here is a definition of scatter-based action recognition. It means recognizing an action solely based on the human scatter sequence. Broadly speaking, using eye landmarks for gaze estimation or using hand landmarks for gesture estimation, and they are all scatter-based action recognition. For scatter-based action recognition, the advantages and the limitations are both quite clear. First, you should use scatter-based action recognition only if it is possible to recognize the action only based on the scatters. A simple counterexample is differentiating several eating something actions. In that case, you can make correct predictions only if you can recognize something. Yeah. While the advantages are scatter-based action recognition is very light and can be more robust than RGB-based ones when training examples is scarce or highly biased. Here we demonstrate the computational efficiency. Scatter-based action recognition is much lighter than RGB-based ones in both parameter size and flops. The table shows that the parameter size of a scatter action recognizer is 10 times less than an RGB action recognizer. Instantiated with the same 3D backbone, a scatter action recognizer can process a 6 times longer sequence with much less computation consumed than an RGB action recognizer. The scattering data fed to the action recognizer can be obtained via various approaches with no need of manual labeling. NTU-RGBD dataset uses a Kinect sensor to collect the 3D scatters, while the collected scatters are noisy and of low quality. Another approach is to use 2D pose estimators to extract 2D scatters in a video. There exist lots of open source pose estimators, such as OpenPose, HRNet, and the user can select one according to the efficiency accuracy trade-off. Besides, the estimated 2D poses usually have better qualities. The third solution is motion capture. One can use mocap devices or vision-based mocap to obtain 3D key point coordinates and use them for action recognition. As a long-standing topic, there exist multiple solutions for scatter action recognition. Generally speaking, there are 2 main paradigms, the GCN-based approach and the CN-based approach. The GCN-based approach uses a spatial temporal graph ConvNet to process the coordinate sequence directly, while the CN-based approach first converts the joint coordinates to pseudo heatmaps, generates a pseudo image with color coding or stack the heatmaps to form a heatmap voxel, and process the pseudo image or clip with a 2D or 3D CNN. Okay, so let's start from the CNN-based approach. Portion is a representative scatter action recognition approach based on 2D CNN. To convert a scatter sequence to a 2D pseudo image, it adopts color coding to squeeze the temporal dimension. A key point at different time steps will be aggregated into a single track heat map, while different time steps correspond to different colors. The track heat maps are concatenated along the channel dimension to form a single 2D image, and then processed by a lightweight 2D CNN. Though carefully designed, the aggregation conducted by Portion leads to severe information loss and inferior recognition performance. To alleviate the drawback of Portion, we propose a 3D CNN-based framework, PYSKL 3D. PYSKL 3D uses 3D heatmap volumes to represent the scatter sequence and uses 3D CNN for scatter processing, keeping all the temporal dynamics losslessly. Basically, the framework consists of 3 steps. First, a top-down pose estimator is used for extracting high-quality 2D poses and save them as coordinates, which contain the locations and the confidence scores of each joint. Second, we generate 2D pseudo heat maps based on the saved coordinates and stack them along the temporal dimension to form 3D heat map volumes. And finally, we adopt an arbitrary 3D CNN to process the heat map volumes and get the action predictions. Let's first look at pose extraction. Pose extraction is a critical step for scatter action recognition, and whose importance is often overlooked. We conduct extensive ablation study on the pose extraction step, and you can refer to our paper for more detailed results. There are 2 main observations. We first find that 2D poses usually have superior quality compared to the 3D ones, which is significant in both qualitative and quantitative studies. Thus, we mainly use 2D poses as inputs in this work. Besides, we also find that action recognition doesn't need perfect pose estimation results, as long as action patterns can be revealed. For example, we can find lots of obvious mistakes in fine-gene pose estimation results, but it doesn't affect the accuracy of scatter-based action recognition. We choose to save the extracted 2D poses as coordinates and restore them to pseudo heat maps in later processing. In experiments, we find that storing poses as coordinates instead of heat maps is a good trade-off. Enormous amount of computations can be saved while the degradation in performance is just moderate. Yeah. And to restore coordinates to pseudo heat maps for each joint, we generate a Gaussian map centered at the joint location. Specifically, in the previous step, we save the location xi, yi, and the confidence score ci for each joint. And now we generate a Gaussian centered at xi, yi with the maximum ci. K Gaussian maps from a pseudo heat map form a pseudo heat map with K channels, while T pseudo heat maps are stacked along the temporal dimension to form a 3D heat map volume. We then propose 2 techniques to handle the redundancy. To reduce spatial redundancy, we find the smallest bounding box enclosing all 2D poses, crop frames with the box, and resize them to a target size. By doing so, more information can be reserved within a small spatial size. To reduce the temporal redundancy, we use uniform sampling to replace the commonly used fixed drive sampling. To get an n-frame clip, we divide the video into n equivalent segments and randomly sample 1 frame from each. We find the new strategy is especially beneficial for scatter action recognition. PostCount 3D can use an arbitrary 3D-CNN to process the heat map volumes, and it's much lighter than 3D-CNs for RGB. We illustrate the PostCount 3D instantiated with slow only. In 3D-CN adaptation, we find two good practices. First, the input should have a small spatial size and a large temporal length. Second, a thinner and shallower network is sufficient for scatter processing. We further propose RGB PostCount 3D for the early fusion of human scatters and RGB frames. It is a 3D-CN with two pathways, processing scatter and RGB respectively. With bidirectional lateral connections, RGB PostCount 3D significantly outperforms the late fusion baseline. To demonstrate the effectiveness of PostCount 3D, we conduct extensive experiments on 9 different scatter action recognition benchmarks. We first compare PostCount 3D with a representative GCN approach, MSG3D. Both approaches take 2D scatters extracted by HRNet as inputs. With fewer flops and smaller parameter size, PostCount 3D achieves strong performance on multiple benchmarks. Beyond strong recognition performance, PostCount 3D also has several unique advantages compared to GCNs. First, it is robust to noises in post estimation. In experiments, we try to randomly drop a key point from each scatter with a certain probability. In such case, the testing performance of PostCount 3D is far better than GCN. Besides, when using poses from different sources for training and testing respectively, PostCount 3D generalizes well across all the settings we tested. Second, PostCount 3D can scale to multi-person scenarios efficiently. In group activity recognition, since multiple scatters occur in the same heat map volume, no extra computation is needed with increasing persons. Meanwhile, the computation amount of GCN scale linearly with the number of persons. Third, using 3D-CN enables a wide design space for intermodality fusion, benefits action recognition with multiple modalities. And combining the key point stream and the limb stream, PostCount 3D achieves the state-of-the-art performance on multiple benchmarks. We also achieve strong performance on action recognition based on multiple modalities, and you can refer to our paper for these results. And here we summarize the advantages of PostCount 3D. In 3D-CN, PostCount 3D is of good spatial temporal modeling capability and has unique advantages in robustness, scalability, and interoperability. Meanwhile, there still exists some worth exploring directions, which includes extending the framework to 3D scatters and better architecture design to improve the efficacy and efficiency. That's all for the introduction of these CN-based approaches. There also exist lots of scatter action recognition algorithms based on GCN. Among them, ST-GCN is one of the earliest and the most representative GCN-based algorithm. Most designs of ST-GCN has been adopted in most of the following works. So we first briefly introduce these general designs. GCN-based approaches directly take the coordinates of human scatter sequences as inputs. When there exist multiple persons, it models each person independently and averages the scatter features before the last classification stage. A GCN recognizer is a stack of multiple GCN blocks. Like a ResNet is a stack of multiple basic block or bottlenecks. ST-GCN stacks 10 GCN blocks for scatter modeling. As the network goes deeper, the channel dimension expands while the temporal dimension shrinks. Each GCN block has a GCN layer and a TCN layer. A GCN layer performs interjoint feature fusion within each single skeleton with a coefficient matrix A, while a TCN layer performs temporal modeling with 1D convolutions for each single joint track. Here we show the implementation of the GCN layer and TCN layer in ST-GCN. You can see that both implementations are quite simple. A TCN layer is just a 1D convolution followed by a BN layer, while the GCN layer consists of a 1x1 convolution for feature transformation and a matrix multiplication for interjoint feature fusion. ST-GCN is a great baseline for skeleton action recognition, but lacks good practices and is not equipped with more advanced model designs. In our recently released code-based PYSKL, we improve ST-GCN in both module designs and the training practices and present ST-GCN++. The old ST-GCN used a single 1D convolution with kernel 9 for temporal modeling, which consumes relatively large amounts of computations and lacks flexibility. In ST-GCN++, following recent works like MSG3D or CTR-GCN, we adopt a multiple branch TCN with different receptive field sizes for each branch. In the new design, assume there exist n branches. The channel width of each branch is only 1/n of the original TCN. By adopting the multi-branch design, both efficacy and efficiency can be improved. For the GCN layer design, the old design adopts sparse coefficient matrix derived from manual skeleton topology for joint level feature fusion and revise the matrix with learnable edge weights. In ST-GCN++, we only use the predefined topology for initialization and keeps the coefficient matrix as learnable parameters. We find the recognition performance can be improved without the sparse constraint. Besides, an additional residual link is added. The new GCN layer design improves the spatial modeling capability while requires few additional computations. Here we summarize other good practices adopted by ST-GCN++. For pre-processing, basically, we follow the recent state-of-the-art CTR-GCN, which includes shifting and rotating to align the center and the spine. It's worth noting that we also adopt uniform sampling for GCN-based skeleton action recognition and find it quite useful. For hyperparameter setting, we adopt the commonly used cosine annealing scheduler and use a relatively large weight K. Here we show the recognition performance of ST-GCN++ on the standard NTU-RGBD benchmarks. The full stream results are reported. We also list the ranking on paper-space code. The improvement is quite significant with all those model designs and good practices adopted. ST-GCN++ can achieve better or comparable performance compared to the previous state of the art. We reiterate that ST-GCN++ is just a simple as strong baseline for skeleton action recognition. It is not a complicated so-called sorter model. The key to the success of ST-GCN++ is quite simple and doesn't rely on any complicated attention schemes, data-dependent coefficient matrix, or other complex modules or training schemes. And if you are interested in PostCon3D or ST-GCN++, the two skeleton action recognizer we presented, you can scan the QR code and find more details in our papers. Besides, all codes for the two models are released in our skeleton action recognition code base, PYSKL. And here is a brief introduction to our newly released code base, PYSKL. It is a comprehensive toolbox for skeleton-based action recognition. It implements two different algorithms and benchmarks them on 9 different data sets. Our implementations are simple, compact, and elegant, with multiple existing or original good practices included. We provide ready-to-go pickle annotation files for users, and you can directly run training and testing for each algorithm with these pickle files. Besides, we also provide tools for scattering visualization and annotation generation for custom video datasets. So after introducing all those powerful scatter action recognizers, there seems to be a depressing fact. The performance on traditional benchmarks seems to be nearly saturated. Most testing cases are correctly classified, and the remaining failure cases are really hard and almost impossible to be recognized by scattering only. So personally speaking, I think the future research in scattering action recognition should focus on the data efficiency and the computational efficiency instead of focusing on improving recognition accuracies on standard benchmarks. First, we talk about data efficiency. It has already been validated that strong recognition performance can be obtained when there exist hundreds of training samples per class. But what if it comes to dozens or even several samples per class? The new setting can be challenging and worth exploring. A possible solution is self-supervised pre-training on massive scattering data. Those scattering data can be automatically generated with pose estimation and massive web videos. Note that the success of data-efficient scattering action recognition may directly lead to lots of customized applications. For example, you can register a brand new gesture with only several video clips, and then the perception system can successfully recognize it. The second challenge is computational efficiency, which is closer to engineering. We already demonstrate that scattering action recognition itself is quite computationally efficient. Combining it with a fast detector and a pose estimator, one can get an efficient perception system for human-centric video analysis, and that can be quite useful. Of course, we know that scattering itself may not be able to handle all action categories, and how to combine scattering with other modalities is also a worth exploring topic. When we combine other modalities with scattering, our goal is to utilize other cues in videos like object or scene, while keeping the good properties of scattering-based action recognition, like the good robustness or the computational efficiency. General multi-stream late fusion may help to improve the recognition accuracy, but most of the good properties do not exist anymore. A simple solution I'm working on is to extend the spatial temporal graph and add diversified features into the graph. For example, we can use object detectors to extract the object features and scene classifiers to extract the scene features and add them as nodes in a larger spatial temporal graph. This framework can be used for various applications such as recognition, retrieval, or self-supervised learning. And that's all for my talk. Thanks for your attention. If you are interested in the introduced topic, you can send me an email or find me at my poster tomorrow. It is at tomorrow afternoon, and my poster is at 40B. And again, thanks for your attention.
Goodbye, everyone.